Welcome back to the Deep Dive. Today we're tackling something, well, fundamental. It might just change how you picture our own solar system, our place in it, maybe even the concept of life itself over cosmic time. Wait, we always talk about the Goldilocks zone, right? That perfect spot, not too hot, not too cold, where Earth sits.
Right, the habitable zone, where liquid water could exist.
Exactly. And we tend to think of it as, well, fixed, like Earth won the lottery and got the permanent beachfront property.
A static location.
But what if it's not? What if that zone is actually moving, like a cosmic spotlight, slowly sweeping outwards over billions of years?
That's the core idea we're diving into today.
We're looking at a paper by scientific investigator Justin Lake, the solar succession hypothesis. And it basically argues that habitability is cyclical. It's a function of the sun getting older.
It really reframes the whole picture.
Okay, let's unpack this. Lake's central argument hits at the very foundation of how we see habitability. He's saying it's not a static address, it's not guaranteed.
No, it's a moving target.
And it's dictated entirely by the sun's own evolution, its slow aging process.
Precisely. So this hypothesis isn't just a neat idea. It's using stellar astrophysics, the known life cycle of stars like our sun, to reinterpret how planets evolve within that changing environment.
So Lake defines habitability as happening in, like, sequential phases.
Yeah.
Epochs.
Exactly. Sequential epochs. As the star matures, as it gets brighter, the zone that's environmentally optimized for life, well, it shifts outward.
Okay, so here's the thesis statement then, boiled down.
Mm-hmm.
Planetary habitability isn't a one-off for Earth. It happens in a sequence, aligned with the star's life cycle.
Yes, a natural progression of habitable worlds over billions and billions of years within just this one solar system.
Which means Earth isn't necessarily the only place life could have arisen here.
We're just the current beneficiaries, the ones renting the optimal apartment right now, so to speak.
That's the big conceptual shift, isn't it? Breaking from that static Goldilocks zone idea.
It is. Because if you think about it, the standard model kind of assumes the zone just sits there. Earth's been in it for, what, 4.5 billion years, give or take?
Right. But Lake is saying, no, the physics demands that the zone migrates. It has to.
And that's based on how stars work. It's not speculation, it's a consequence of stellar physics.
So if it's migratory, that changes everything.
It completely changes where we might look for past life or even future life within our own system.
You mean places like Venus, which is, hellish now?
Could have been pleasant, could have had liquid water in the deep past when the sun was dimmer. Yes.
And places like Mars? Currently frozen.
Might be on deck for their habitable phase in the distant future.
Wow. Okay, so our mission today is really to trace this cycle, to understand how the sun isn't just the giver of life, but also, eventually,
the executioner. It dictates the lifespan of habitability on each world sequentially.
Let's get into the engine then, the mechanism behind this. Lake calls it the migratory habitable zone model.
Right, and it all starts with the sun.
The sun's getting brighter over time. That's the key, isn't it?
That's the absolute core principle. And Lake cites the standard astrophysical understanding here.
Which is?
That a star like our sun increases its luminosity, its brightness, by roughly 10% every billion years.
10% per billion years.
Yeah.
Okay, that might not sound like a huge jump year to year.
No, it's incredibly slow, imperceptible on human timescales.
Yeah.
But over the lifespan of the solar system.
That's a massive change. It adds up.
It really does. Think compound interest, but for stellar energy output.
We should probably touch on why it gets brighter, though. It's not just running hotter randomly.
Not at all. It's fundamental fusion physics. Mm-hmm. The sun is fusing hydrogen into helium in its core. That's its power.
Okay.
But helium is heavier than hydrogen. So as this helium ash builds up in the very center, the core becomes denser.
Denser, okay.
And this increased density cranks up the pressure and temperature in the surrounding hydrogen-burning shell. It forces the fusion to happen more intensely, more efficiently.
Like squeezing the engine to make it run hotter.
That's a good way to put it. The core contracts slightly under the weight of helium, the fusion rate goes up, and the star's overall energy output, its luminosity, increases. The outer layers expand a bit and radiate more energy.
And this is just the standard main sequence evolution for a star like the sun. It's not controversial physics.
Not at all. It's well-established stellar modeling. It's just the long-term consequence of burning its fuel.
Okay, so if the sun is slowly turning up the heat, like a giant dimmer switch going brighter,
then the zone where temperatures are right for liquid water, the habitable zone, it can't stay put.
it has to move outwards. away from the increasing heat.
Exactly.
Yeah.
To maintain those just right temperatures, you need to be further away from the brighter star.
Which creates this ripple effect across the planets.
A very systematic, very slow, but inevitable sequence.
So the inner planets,
Yeah,
they get the heat first.
right. Planets that might have been in the sweet spot early on when the sun was maybe 70% or 80% as bright as it is now.
They eventually cross the inner edge of that moving habitable zone.
And they transition from potentially habitable to, well, uninhabitable. Runaway greenhouses, surfaces baked, atmospheres potentially stripped.
They get cooked.
Essentially, yes. They fall victim to the increasing solar radiation.
But, and this is the optimistic part of the hypothesis, right?
Mhm.
As the inner worlds overheat,
The outer worlds are simultaneously moving into the zone from the cold side.
they start to thaw out.
Correct. Worlds like Mars, currently too cold for stable liquid surface water, begin to receive enough solar energy as the habitable zone migrates outward towards them. They approach potentially optimal conditions.
So the idea is that the solar system might always have had a potentially habitable world, just not the same one.
That's a key implication. Habitability itself might be persistent, even if it's migratory.
And the time scale here is just immense. We're not talking centuries or millennia.
We're talking billions of years,
Yeah.
giga-year timescales, which fundamentally changes how we should interpret the planets we see today.
So looking at Venus's current state doesn't necessarily tell you its whole story.
Exactly. You might be looking at a planet whose habitable era ended billions of years ago. Its story was written, and the book closed, long before Earth's most complex life even emerged.
Okay, the physics makes sense. The zone moves. So, who lived where and when? This takes us to the really juicy part, right?
This is the temporal life sequence hypothesis.
Here's where it gets really interesting, because Lake doesn't just say the zone moves. He assigns potential biological phases to specific planets in a specific order.
He aligns each terrestrial planet's potential prime time with a specific solar epoch following that outward migration.
And it's counterintuitive because we're so used to thinking Earth is the place.
We have to think chronologically, following the young, dimmer sun outwards.
So where does it start? Mercury.
Lake proposes Mercury might have had what he calls a proto-biospheric stage, very early on.
Proto-biospheric, meaning?
Meaning if life got started there, it was likely very simple, very early, and probably didn't last long. We're talking the solar system's infancy, maybe the first few 100 million years.
When the sun was significantly fainter, maybe 70% of current brightness.
Around that, yes. The habitable zone would have been much, much closer to the sun than it is today. Mercury might have been within it.
But Mercury's so small, so close to the sun now, it seems impossible.
Now, yes. But back then, with a dimmer sun, perhaps a thicker early atmosphere derived from outgassing, maybe some internal heat, it's conceivable it had a brief window.
Brief being the key word.
Extremely brief. Before the sun ramped up, the solar wind intensified, and any chance of surface habitability was scoured away. It was likely the first potential niche and the first to be extinguished.
Okay. So after Mercury's brief shot, the zone moves outward to
Venus. And this is where the hypothesis gets really provocative.
because Venus today is, well, it's hell. Surface hot enough to melt lead, crushing pressure, sulfuric acid clouds.
The least habitable place imaginable, maybe?
Yet Lake suggests Venus experienced its prime biological phase, its golden age.
Yes. And he puts a time frame on it. Roughly 2 to 3 billion years ago.
2 to 3 billion. That's a
Okay.
long time ago.
A very long time ago. Think about what Earth was like then. Maybe complex single cells, eukaryotes just emerging. Life was here, but simple.
And during that period, Venus was potentially Earth-like.
That's the implication. 2 to 3 billion years ago, the sun was maybe 75–80% as bright as it is today.
Which puts Venus's orbit.
Potentially right in the middle of the habitable zone at that time.
So you could have had liquid water oceans, a reasonable atmosphere.
It's thermodynamically plausible. It might have had vast oceans, a dense atmosphere, maybe more CO2 than early Earth, keeping it warm under a dimmer sun, but not yet the runaway greenhouse we see today. Stable surface temperatures conducive to life.
A potential paradise, billions of years before Earth hit its stride.
A completely different Venus than the one we know. And the transformation from that potential cradle of life to the inferno we see today is presented as the direct result of the sun's evolution.
That relentless 10% per billion years.
Exactly. As the sun continued to brighten, Venus received more and more energy. Water vapor, a potent greenhouse gas, would have increased in the atmosphere.
Mhm.
Yeah. More heat means more evaporation, which means more water vapor, which traps more heat. It's a positive feedback loop.
The runaway greenhouse effect.
Precisely. At some point, Venus crossed a threshold. The oceans boiled away, the atmosphere thickened massively with CO2 released from rocks, temperatures soared. Lake called it solar execution. The increasing brightness killed Venusian habitability.
Wow. Okay, so Venus had its time, then the sun turned up the heat and its window closed,
And the habitable zone continued its outward march.
reaching Earth. Our turn.
Right. So in Lake's sequence, Earth represents the mid-cycle habitability stage. We are the current beneficiaries. We're in the zone now.
We're living in Earth's crime.
We are, for complex life anyway. The conditions have been relatively stable for hundreds of millions, even billions of years.
But the scary part is if this sequence holds, our time is also limited, isn't it?
That's the sobering implication. We are following the same path as Venus, just, delayed because we're further out from the sun.
That 10% per billion years increase doesn't stop for us.
It doesn't stop. Eventually, Earth will receive too much solar energy. The oceans will start to evaporate significantly. The greenhouse effect will strengthen.
We'll face our own runaway greenhouse.
Lake estimates this could become a serious issue for complex life, potentially starting within the next, say, 500 million to a billion years. It's not immediate, but on planetary timescales, it's the next step.
So, after Earth's time is up, the zone keeps moving outward,
Towards Mars.
which Lake defines as the future candidate.
Yes, Mars is next in line for optimal conditions, according to this hypothesis.
Right now, Mars is cold, dry, thin atmosphere. But we know there's a lot of water ice there, right? Underground.
Vast amounts, yes. Locked up as permafrost and potentially in subsurface reservoirs.
So as the sun continues its slow brightening over the next billion years or more,
Mars will start receiving significantly more solar energy, enough, potentially, to begin thawing those ice reserves.
could that release water? Maybe gases to thicken the atmosphere?
That's the potential pathway. Thawing ice could lead to liquid water, maybe temporary rivers or lakes. Outgassing of CO2 and other volatiles trapped in the ice or rock could gradually increase atmospheric pressure and warmth.
Creating a Martian climate that could eventually support stable liquid water on the surface.
Potentially, yes. Long, long after Earth has become too hot, Mars might inherit the habitable zone billions of years from now.
So the full sequence is Mercury's early flicker, Venus's ancient prime, maybe 2-3 billion years ago, Earth's current golden age, and then Mars's distant future.
That's the temporal progression proposed by the solar succession hypothesis. It paints a picture of our neighboring planets not as static failures or successes, but as different acts in a long, unfolding solar system drama.
Okay, but this leads to the big question. The elephant in the room.
The lack of evidence.
Exactly. If Venus was potentially a paradise with oceans 2.5 billion years ago,
Well.
first the proof. Where are the fossils, the ruins, anything?
It's the obvious and critical challenge to the hypothesis, and Lake addresses it head-on.
He must have anticipated this.
Absolutely. He introduces a concept specifically to explain this apparent contradiction, the planetary erasure principle.
Planetary erasure principle.
Okay, what does that mean?
It basically argues that the very processes that occur on planets, especially when they undergo drastic climate shifts driven by their star, are incredibly effective at destroying or burying the evidence of past life over geological time.
So the lack of evidence isn't necessarily evidence of absence?
Correct. It might be evidence of very efficient geological and atmospheric recycling and destruction. The planet itself wipes its own slate clean.
How does this work? Are there specific mechanisms?
Lake highlights two major ones, tailored to the specific planets and their fates. First, for Venus, it's Venus's resurfacing.
Resurfacing, I've heard about this. Venus's surface is surprisingly young, geologically speaking.
Extremely young. Estimates suggest the average surface age is only around 500 million years, maybe a bit more, which is bizarre for a planet as old as the solar system.
Why is it so young? The leading theory is that Venus lacks Earth-style plate tectonics. On Earth, plate tectonics constantly recycle the crust and release internal heat gradually. Venus doesn't seem to have that.
So the heat builds up inside.
It builds up and up and up until, perhaps catastrophically, the planet undergoes massive global volcanic eruptions. The entire surface gets repaved with lava flows.
A planetary reset button.
Exactly. Imagine the entire surface of the planet being buried under kilometers of fresh volcanic rock every 500 million years or so.
So any evidence from 2.5 billion years ago, fossils, structures, chemical signatures.
Would be obliterated, crushed, melted, chemically altered by the intense heat and pressure in an acidic environment, and then buried deep beneath the new surface.
You literally can't find the evidence because the ground it was on doesn't exist anymore, at least not at the surface.
Precisely. Looking for 2.5 billion-year-old biosignatures on a 500 million-year-old surface is, well, futile. The geological process itself erases the history.
Okay, that's a powerful argument for Venus. What about Mercury? It didn't have massive volcanic resurfacing like that, did it?
Probably not on the same scale. For Mercury, Lake invokes the second mechanism, solar stripping.
Because it's so close to the sun.
So close, and it lacks a strong global magnetic field like Earth's, which protects us.
Right, our magnetic field deflects a lot of the solar wind.
Mercury doesn't have that shield, or only a very weak one, and it's right there, bathing in the intense radiation and particle flow from the sun.
Especially as the sun got brighter over time.
Exactly. The intensifying solar wind energetic particles streaming from the sun would have relentlessly scoured Mercury's surface and stripped away any primitive atmosphere it might have had.
Blasting away the evidence.
Essentially, yes. Bombardment by solar particles, micrometeorites, and intense UV radiation over billions of years would erode the surface and break down complex molecules, including any potential organic biosignatures from that very early proto-biospheric stage.
So even if simple life flickered briefly on Mercury 4+ billion years ago,
the record has been sandblasted away by the sun itself. It's a different erasure mechanism than Venus's, driven by proximity and lack of protection, but equally effective over deep time.
So the planetary erasure principle combines these geological and atmospheric destruction mechanisms.
To argue that the absence of observable evidence on Mercury and Venus today is actually expected under the solar succession hypothesis. It doesn't disprove a habitable past. It reflects the natural consequences of stellar evolution, acting on planetary surfaces over billions of years.
The silence isn't proof of absence. It's proof of the destructive power of time and stellar change.
That's the core idea of the principle. It's a way to reconcile the potential for past life with the barrenness we observe now.
This is really shifting my perspective. Okay, so if life itself follows this sequence, what about intelligence?
Yeah.
Civilization?
Now we move into perhaps the most profound and speculative part of the paper, the anthropic implication.
Anthropic, relating to humans or intelligent life?
Exactly. If the potential for basic life is sequential, moving from planet to planet, then Lake argues the potential for intelligent life or civilization must also be temporally staggered.
Temporally staggered, meaning not happening at the same time.
Right. Each planet gets its window of opportunity, not just for microbes, but potentially for complex life and intelligence to evolve. But those windows open and close sequentially.
So, Venus might not just have had oceans. It might have had Venusians.
It's a possibility allowed by the hypothesis. An intelligent civilization could have arisen on Venus during its prime habitable phase, 2 through 3 billion years ago.
And they would have lived, developed technology, built cities.
And then eventually faced an unavoidable existential threat as the sun kept brightening and their planet turned into an oven.
Their entire civilization wiped out by climate change driven by their own star.
An externally forced extinction event on a planetary scale. This offers a potential, somewhat chilling solution to the Fermi paradox. Where is everybody?
Now, why haven't we heard from aliens?
Well, maybe we missed them. Not because they're far away in space, but because they existed right next door just billions of years ago in time. Their signals died out long before we evolved ears to listen.
We're ships passing in the cosmic night, separated by eons.
That's one way to look at it. It suggests intelligence might be common, but its emergence and persistence are strictly constrained by the habitable window granted by the parent star.
This paints the sun in a really complex light, doesn't it?
Absolutely. In Lake's framework, the sun plays this incredible dual role. It's the progenitor. Its energy makes life possible in the first place.
But it's also the executioner.
Its inevitable evolution, its brightening, ultimately destroys the very habitability it initially created on each inner world. It gives life and it takes life away, planet by planet.
That changes how we should even think about searching for past intelligence then. SETI, looking for radio signals.
Might be looking for ghosts that vanished billions of years ago. The erasure principle suggests any artifacts or easily detectable signals would likely be long gone.
So what should we look for, according to Lake?
He suggests looking for more subtle, deeply buried, or indirect evidence, maybe large-scale geological anomalies that are hard to explain naturally. unusual isotopic ratios in rocks, perhaps remnants of massive engineering projects that somehow resisted erasure, buried deep below the surface.
Looking for the scars of a lost civilization, not its messages.
Something like that. It's a much harder search, obviously,
Yeah.
but it redirects the focus from active contemporary signals to archaeological or geological forensics on our neighboring worlds.
If this hypothesis holds up, it completely rewrites the roadmap for exploring our solar system.
It really does. Venus stops being just a failed Earth and becomes potentially Earth's predecessor. Mars stops being just a cold desert and becomes Earth's potential successor.
They become chapters in the same story.
Yeah.
Venus is the past, Mars is the future.
And we on Earth are the present chapter. We might be the civilization that replaced a long-gone Venusian one.
And we might eventually be replaced by a future Martian one, assuming life takes hold there.
It puts humanity in a very different cosmic context. Not necessarily unique, but perhaps unique to this time. We're renters in this cosmic timeshare, as you put it earlier.
That timeshare analogy really sticks. It makes the silence of the universe feel less like a paradox.
And more like just bad timing. Or maybe perfectly natural timing within this grand, slow, stellar cycle.
Okay, this has been a lot. Absolutely fascinating. Let's try to bring this back to the surface, summarize the key takeaways for everyone listening.
Sounds good.
So, what does this all mean? We dove into scientific investigator Justin Lake's solar succession hypothesis, and the first big takeaway is, forget the fixed habitable zone,
It's migratory and has to move outward as the sun evolves.
driven by that core mechanism. The sun getting about 10% brighter every billion years due to natural stellar physics, the buildup of helium in its core,
Right, that increasing luminosity forces the temperature sweet spot further out over time.
which leads directly to the temporal life sequence, the proposed order of habitability.
Mercury's brief early window, then Venus's prime maybe 2-3 billion years ago, then Earth right now in our mid-cycle phase, and finally Mars as the future candidate billions of years from now.
And the crucial counterargument to where's the evidence is the planetary erasure principle.
Yes, the idea that natural planetary processes, catastrophic resurfacing on Venus, intense solar stripping on Mercury, effectively destroy or bury the evidence of past biospheres over these immense timescales. The lack of evidence is explained by the model.
And the implication for intelligence. Just, wow, civilizations might rise and fall sequentially.
Temporally staggered, we might have had predecessors right next door, lost to time and stellar evolution. The sun as both creator and destroyer.
So Lake's paper isn't just about planets. It's about time, persistence, and maybe our own place in this long cosmic relay race.
Exactly. It suggests every terrestrial planet tells part of the story. Each bears silent witness to this cycle of life being granted and then ultimately revoked by the star they orbit. We might find echoes of our past on Venus or glimpses of a potential distant future for life on Mars.
Which leads us with a final, really provocative thought for you, the listener, to mull over.
Go for it.
If we accept this idea, even hypothetically, that Earth is the mid-cycle civilization, we inherited this habitable window after Venus lost its chance. What might a civilization achieve in its prime window, maybe 1 billion or 2 billion years of relative stability, before the star inevitably forces its decline?
What level of technology, philosophy, art, what understanding of the universe could they reach?
And what traces, what knowledge might be utterly lost, buried under Venus's heat and pressure, erased forever by that planetary reset button? Could they have known the cycle? Could they have tried to warn whoever came next?
It's mind-boggling to consider, and it flips the question forward, too.
How so?
Well, knowing this potential cycle, what responsibility does that place on us, the current tenets? Especially regarding Mars, the potential next habitable world in the sequence. Does our understanding of this deep past inform our actions regarding the deep future?
Are we just passive observers in this cycle, destined to fade out like potential Venusians before us? Or do we have a role in, I don't know, seeding the next chapter, ensuring life's persistence in the system?
The hypothesis suggests the succession is a natural process driven by the sun. But our awareness of it, that adds a whole new layer. What will Earth's legacy be in this solar succession?
A question with no easy answers. Something to think about long after this deep dive ends.